Swayam Prabha. Digital India. Educated India.
So mathematically we said something like, there is a function that can be given as a mapping function that depends on time, natural variable time, and some random variable x. Then we say what this x is, okay, whether it is a uniformly distributed random variable or a Gaussian or an exponential, whatever it is, okay. So now the response of this function y will have different outcomes. For the same time point, it has many outcomes, okay. So that's what we say, the system is evolving in time but probabilistically, okay. That's the characteristic of a stochastic process. Now if you look at this, then there are a lot of classifications, okay. For example, there is something called Bernoulli trials, there is martingales, and there are Markov processes, okay. And this is a very widely studied subjects in mathematics, but since we are talking about engineering application of stochastic process, a large set of problems from physics, chemistry and engineering comes under the category of what is called the Markov process, okay. So Markov process is a subset of a stochastic process. It has a particular characteristics and attributes that makes this very, very useful for applying to engineering problems, okay. So rest of the course we are going to discuss Markov process. Markov process can also come in two other possibilities. It can be a continuous Markov process or it can be discrete Markov process, okay. Again, in the context of engineering applications, we are going to restrict our attention to only those problems, okay. So from here we are going to talk about Markov process. So Markov is a name of a Russian scientist who developed a lot of theory for this, so we associate to his name. So we are saying that Markov process is a stochastic process with some more simplification with certain properties, okay. So that's what I want to discuss today to kind of formally introduce what is a Markov process is and what the Markov properties are, okay. And later on I will give you some example, how do you think about a Markov process for a given physical system or physical chemical system. So this basically I am going to go back to the very first classes where I talked about joint distributions, marginal distributions and the conditional probabilities and stuff like that. But here I am going to bring this time element also, okay. In the very first class I was only talking about static probability distributions which does not have any time signature. We can actually define the same set of hierarchical distributions with the time encoded, okay. So therefore we apply these formulations for stochastic process. Since we are talking about time, it is probably a good idea to actually think about n successive times such that we have t1 less than t2 less than t3 and so on so. Okay, we are interested in dynamical response of a system at some time point t1, t2, t3 such a way that the time is increasing in one way, okay. So then we say that a total joint probability distribution of n variables x1, x2 all the way up to xn as Pn x1 t1, x2 t2, xn tn. So what we are saying is there is a stochastic process and its state is defined by a set of random variables x1, x2, x3 all the way to xn. Each of this variable corresponds to corresponding times. So x1 is defined at t1, x2 is defined at t2 and so on so. when I look at the sum of, when I look at the collection of all these x variable, that basically gives me the dynamical evolution of the system over a period of time. Okay. So, we define a function called the total joint probability distribution function for a stochastic process having n time instances. Okay. So, here the way that I write is, I am actually setting x1 comma t1. It says the value of the random number x1 is taking a numerical value x1. So, the small x1 means the realization. Capital X, these are random variables. Random variables can take set of possible values. So, here at time t1, what is the probability that the system will be found at a numerical value of x1, and another time x2, what would be its value x2, and so on, so on, all the way up to n. Okay. So, this basically tells you a probability of a trajectory from time t1 to tn. Okay. So, if you think x is the position of a Brownian particle, then we are talking about the one dimensional random walk of a Brownian particle as a discrete set of time. Okay. So, this if I have to plot, this is time, this is x. Okay. So, this can be one trajectory, and this function is a probability of finding this trajectory. Okay. For every trajectory, we can define a probability distribution function. Okay. And another possible trajectory can be this. Okay. So, the way I am drawing is a set of x1, t1, x2, t2, and so on. So, instead of drawing these trajectories, we can define the trajectories as a mathematical function or a probability distribution function, which we call it as a total joint probability distribution function. It completely specifies the system's dynamical evolution. Okay. If you specify all this, it basically tells you what is the complete nature of the system, dynamical system. Now, like I said, you can have joint distribution, then we can also think about a marginal distribution by integrating out certain variables. Let us say you are not worried about the state of the system at some other time, and you are only worried about what is the state of the system in some finite space, okay, or in the reduced number of variables. Okay. So, that basically brings us to what is called this marginal distribution, okay, where we are going to integrate out certain variables and keep the other one dependent. So, we are saying that the total joint distribution function gives the entire information from t1 to tn. Okay. Now, let us say you are asking, I am not interested for the entire trajectory, I am only interested a part of this trajectory. Okay. What is the likelihood of finding only part of the trajectory? Then what we can do, we take this total joint distribution function and integrate out other variables that we are not interested in. For instance, I am only interested from t1 to ts, where s is less than n. N is the total number of trajectory points, S is a subset, and we are asking what is the probability, what is the joint probability of this particular trajectory. Okay. This signifies only part of the trajectory, and we can obtain that by integrating out the total joint distribution function for the remaining variable. So, from s plus 1 onwards up to n, we are integrating out. Okay. How many dimensions are there in the integral? N minus s, n minus dimensions are there, okay, because for each variable you are integrating, and we call this as the marginal distribution distribution function. Then there is something called conditional probability. Conditional probability of x1 all the way up to xs given xs plus 1 all the way up to xn. And we denote this as ps given n minus s x1 t1 xs ts conditioned with xs plus 1 ts plus 1 . So the third important function we are saying is conditional probability of random variable x1 to xs given that, specifying that the remaining s plus 1 to sn. Okay. There is a difference between the marginal and the conditional. In the marginal, we do not specify the other variable from n, s plus 1 to n. We are saying whatever value it can take, that is fine. I am only interested in from variable x1 to xs, okay, that is marginal. But here in the conditional, we are not freely saying any possible value for the remaining variables. We are specifying that from s plus 1 to xn, I am specifying these are the values. Given that, what is the probability of the remaining variables? So here we use a different notation here. N minus 1 variables are specified, and then we are asking what is the likelihood of finding s variables. So that is this notation. Okay. From this vertical line, this tells you how many number of variables you are fixing, you are prescribing, you are conditioning, and this variable tells you how many variables you are asking for its evolution, dynamical evolution. Yeah. So we are actually looking at discrete times in those cases, right? Time is not, we are not integrating over time. We are actually looking at in those specified time what is the outcome is. Ts plus 1, okay. No, what we're trying to say here is that we are trying to identify the state of the system at discrete set of points, okay, and then we are asking in those fixed time. That's what I'm saying. I'm looking at some discrete time already, okay. So we are not doing a time averaging here yet, okay. So for the sake of definition, we do this. Later on, the time can come into an integral part of the evolution itself, okay. So right now we are trying to just set the platform for our definition point of view. Okay, so I hope any question on these things. So we are defining three functions, right? The total joint distribution function, the marginal, and the conditional. The only difference between this approach and the one we defined in the beginning was we are bringing time into this formulations. Earlier we did not have time, okay, because we are talking about stochastic process. There is a time signature. So now after defining this conditional probability, now we can state what is a Markov process. So suppose if I can write that P xn tn given xn minus 1 and tn minus 1, xn minus 2, tn minus 2, all the way up to x1 and t1. Our general definition of conditional probability is this, that I have n discrete points to observe the system, out of which I am specifying n minus 1, and I am asking what is the probability of finding the remaining s variable. Okay, and that's how we write this. We are conditioning n minus 1 variables, and we are asking what is the probability of finding x1 to x's. This is the general definition of conditional probability. Now let's say I define another function where I specify n minus 1 variables, and I am asking what is the outcome, or what's the probability of one trajectory point. From x1 to xn minus 1 I specify, and I ask what is the probability of finding the next time point at xn. Okay, we are giving the entire history up to tn minus 1. What will be the next? So what's the future of this? Okay, conditioned over n minus 1 variable, what is the probability of finding the next instance? Suppose if I can write this as this function where the outcome xn depends only on n minus 1, xn minus 1, and nothing further. Okay, so this is a kind of a special property. A conditional probability depends only on the current state, not any past. Okay, we say it is memoryless. It does not depend, it doesn't know what it did at n minus 2, n minus 3. The path is forgotten, the memory is forgotten, right? If there is a stochastic process for which the conditional probability can be written simply as this, then we say this stochastic process is a Markov process. Okay, we say this is a Markov process. Let me repeat one more time. When we write a conditional probability by specifying n minus 1 terms and asking the probability of the nth term, there are some special kind of process where this conditional probability depends only on the immediate past, not the distant past. Okay, xn depends only on the previous value n minus 1, nothing beyond. It doesn't depend on n minus 2, n minus 3. If there is a stochastic process that has this kind of a conditional probability, we say that is a Markov process. How does it help us? How can this be useful for us? We don't have to store the long history. If I want to look at, if I start from some place, I know what is the next outcome is going to be. Once I update my time, I can actually sequentially I can update my system based on my current value. Okay, so the entire joint distribution can be constructed once you know this transition probability, because you don't need to know all the past, you only need the current position or the current state, and with that we can construct the entire hierarchical joint distribution function. So that's how it becomes very useful. Suppose if you don't make this approximation, we won't be able to construct the entire joint distribution simply. Okay, so that's basically a big advantage. Let me show that with an example. So we say that P11 xn tn xn minus 1 tn minus 1. This conditional probability we call it as a transition probability. We give a special name. Okay, so we are saying the transition probability is a subset of a conditional probability. That means a transition probability is also a conditional probability, but the transition probability depends only on the one state. It doesn't depend on the past. Okay, so we say this is a transition probability of a Markov process. So then what we can formally define is, we can define a Markov process. Markov process is defined by two functions. One is this, and P1 by 1 xn tn xn minus 1 tn minus 1. So, Markov process is something that is defined completely by specifying two functions. One, that is the probability of finding x1 at t1. This is like initial state, you have to start somewhere, okay. You need a starting condition, like in ODE, in PD we talk about initial conditions, right. The same way here, we have to initiate the probability for a time t1 using based on the single point distribution. This is like initial condition. Once we know this, and then we have this Markov property for the transition probability. So, only these two are required for you to construct the entire total distribution function. Okay, so we define Markov process with these two functions. Now, let us consider a 3-point system that I am looking at a dynamical evolution of a system at 3 time points t1, t2, t3, such a way that t1 is less than t2 and t2 is less than t3, and my joint distribution function basically is this: x3 comma t3, x2 comma t2, x1 comma t2, right. So, here I am just defining the total joint distribution function that tells you for this time ordering what is the dynamical evolution of a system, okay. So, now we can write this as the following, that we first say p1 2 x3 comma t3 conditioned with x2 comma t2 x1 comma t1 times the probability 2 x2 comma t2 comma x1 comma t1. So, what we are saying is this joint distribution function we are trying to write in terms of conditional probability, that if I know here this is a 3-point distribution, right. I am looking at 3 time point distribution, okay. I am writing this 3-point distribution is equal to a 2-point distribution on 1 and 2, okay, and then a conditional distribution that given that x1 t1 and x2 t2, what is the likelihood of x3 and t3, okay. So, we are writing a total joint distribution function using conditional probability. This is something we do all the time in our probability course, that a total function can be written in terms of conditional probabilities. A 3-point distribution is written in terms of 2-point distribution times the conditional probability, okay. All of you are with me here? Do you know how we write this? I would have written exactly the same expression before without the time signature, okay. Now, like I have split this, I can also split this, isn't it? I can also write this 2-point into a 1-point and times a conditional probability. So, let me write P2, that is x2 comma t2, x1 comma t1. I can also write this as probability of a single point, which is t1 x1 t1 times transition probability that is conditioned at x1 and t1. So, what we are saying here is a 3-point distribution is written in terms of a 2-point distribution and the corresponding condition probability. Similarly, the 2-point can be written in terms of 1-point distribution and the corresponding transition probability. I already mentioned that the single point is defined and then the transition probability also defined. So, that means we know exactly this, okay. We have defined both the single point as well as the transition probability. Now, we can actually substitute that here, so that this P3 becomes, I write P3 and then this argument is entirely the same as this. Now, when I look at this, if this is a Markov process, how can I write this? This says that I am conditioning 2 previous time points. I am asking what is x3. If this is a Markov process, how will this be written? This depends only on x2, t2, does not depend on x1 and t1 anymore, because this is where we are using the Markov property. So, we are saying this becomes P, it does not depend on 2 previous time points, it depends only on the just previous time point. So, this becomes x3 t3 conditioned at x2 t2. And then for the P2 I can substitute this, that is P11 x2 t2 conditioned at x1 t1 times P1 x1. So what we are saying is that a 3-point distribution can be simply written as a single point distribution for x1 and subsequent multiplication of transition probabilities from x1 to x2 and x2 to x3 and x3 to x4 and so on. So that means for any large trajectory, for any n, you should be able to write this kind of a recursive relationship, and this is only possible because we were able to simplify this transition probability. If this was not the case, we won't be able to write like this. We still need the explicit transition probability that depends on the past. Okay, so that's why the Markov process become very useful to reconstruct a joint distribution function by simply a hierarchical multiplication of individual transition probabilities. So therefore, if you want to generalize this, you can say n point distribution, okay, can be single point distribution P1 x1 comma t1. This symbol means a multiplication of a series of P11 x I plus 1 t I plus 1 given xi ti, and here I goes from 1 to n, or sorry, n minus 1. All right. Okay. So to summarize, what we are saying is that for any stochastic process, we define a joint distribution function that tells you the probability of finding a trajectory, which is basically a sequence of states at a sequence of time, and that joint distribution function can be written as a kind of a multiplication of many transition probabilities, provided that the transition probability follows this Markov property, which is this. Okay, so that's why we are saying that a Markov process is a subset of a stochastic process because of the simplification. Okay, so next thing now we want to do is when do we this kind of a situation? For what kind of processes the transition probability depends like this. Okay, so now what happens is that this is where things become a little bit kind of dicey, that for a given process you can always find a condition where this Markov property is valid, okay, and for other instances it may not be valid. So many times it is something we have to argue that a process can be modeled as a Markov process under certain conditions. Okay, to give an example, let's say that we have a Brownian particle, okay, and this Brownian particle, we know that it is a large particle suspended in a liquid, and this liquid molecules are giving these kicks, and then this particle is moving. Okay, so when you make an observation of this Brownian particle, we can look at their velocity, we can look at their positions. Okay, now let's look at the velocity alone. Okay, now between subsequent time points, if you look at, you see that the particle have a velocity which doesn't remember its past. Okay, there is no correlation of the velocities between this time point and the previous time point. If you are making an observation over a time period where the velocities does not seem to be correlated, then we can say the Brownian particle's velocity is a Brownian process. But if your observation is very, very narrow, very quickly you are making an observation, so then the particle will remember what happened in the previous subsequent collisions, and the velocity may not be actually decorrelated. Okay, so we talked about autocorrelation function, right? And if you look at velocity autocorrelation function, there is a time scale at which this velocity autocorrelation function decays. If your observation time is lesser than that of the correlation time, then it will remember all the past collisions and the past velocity changes. Then in those time scale, you cannot say that the Brownian particle is a Markovian process. It will be a non-Markovian process. That means as a user, as a modeler, we can always think about a time scale where the velocity autocorrelation function is died out already, and you are making an observation at a longer time scale. In that observation period, your process can be a Markovian, right? So, and similarly, if you think about a reaction, okay, a reaction, a molecule A is decomposing into, two molecules. So, in this reactive process also, we can think about, again, based on the time scale of observation, we can say whether it's Markovian or non-Markovian, okay. In this case, what happens is that if you look at if you make an observation at a certain regular intervals, and you see that the number of molecules seems to be a uncorrelated number, it depends only what was before and nothing beyond. If it doesn't know the history, then you can say that it is a Markovian reaction process. Or if you want to say in other words, let's say you look at how the molecule is actually climbing the potential surface because it has to overcome the activation energy barrier. The walk on the potential surface is a random walk. The molecule will go up and down, up and down. So if you look at the trajectory, it will become a random walk like, okay. So in that vibrational states also you can see that the molecule can be approximated as a Markovian. So many times it comes to us to define under what time scale a process can be defined as a Markovian or not, okay. So that's where it is a little bit challenging, okay. So we have to look at the process. If it's a physical or chemical process, we have to look at what are the things that are affecting. Is there a time scale where I can see all the variables are decorrelated, and in such a case you can define them as a Markov process. If you are making an observation which is too short, in which the internal dynamics are actually controlling each other, then we say that it is not a Markovian anymore, okay. Now if you have a kind of a domain where such argument can be made and then you can define something as a Markovian, then all these things can be used to describe the trajectory, okay. So and typically the way that one should do is you look at all the possible Markov process in the literature and learn and see under what circumstances they have used this as a Markovian. When a new situation comes to you and you want to model it, and you have to put yourself into this argument that in what time domain, in what level of coarse graining of the time can I think of this as a Markov process or not, okay. So that becomes a little bit an open-ended for you to think about. Now one more thing I want to introduce to you is this consistency test for a Markovian process. Okay, so let's say there is a process and then you thought about the dynamics, all the physical aspects, and then you say that there is some particular time domain where I can think of this as a Markov process. Once you say it's a Markov process, let's say you come up with these definitions of transition probabilities. Then validation or testing of that assumption is that there is an equation called consistency equation or a Chapman-Kolmogorov equation that has to be followed if it is truly a Markov process, okay. And that basically goes as something like this. So consistency test. So this is called the Chapman-Kolmogorov equation. So let's say that for time t1 less than t2, and in this ordering of time, we have p3, x3 t3, x2 t2, x1 t1. This is something we wrote before as this. So 3-point distribution based on the transition probability, we wrote that the single point distribution times the transition from x1 to x2 times from x2 to x3. Okay, this we wrote before. Now what we can do is we integrate this with respect to all possible x2. So integrating over x2 dx2. So this can be taken out of the integral, whereas these two will become inside the integral. And then you can bring this down, and then you get so when we do this, remember that we talked about the marginal distribution, right? So here I have x1, x2, x3, that's a joint distribution. I am integrating out with only with x2. What do I get is a marginal distribution of only x1 and x3. Okay, if you go back to the initial discussion where we talked about the marginal distribution by integrating out certain variables. So here we are integrating out with respect to x2. So what you will get here is p2, x3, t3 and x1, t1. Okay, so you get a marginal distribution when you do this integral, and then you bring this down p1, x1, t1. What do you think is this? What is this? Conditional probability given x1 t1, what's the probability of getting x2 t2? So this basically nothing but a conditional variable, conditional probability p11, x3 t3 condition at x1 comma t1. Okay, and that must be equal to this. Let me again walk you through here. So what we are trying to do is, I have three discrete time points t1, t2, t3, and I am writing what is the joint distribution function between t1, t2, t3. This can be written based on the transition probability of a Markov process, single point distribution times products of two transition probabilities. Given x1 t1, what's the probability it will go to x2 t2? Given x2 t2, what's the probability it will go to x3 t3? So this we know how we wrote. This is based on the Markov property of the process. Then what we are saying is, we take this equation and we integrate over the middle point, which is x2 t2. Okay, when I do that, on the left hand side I have a joint distribution function. I am integrating with respect to one variable, that gives me a marginal distribution of only two variables, that is x1 and x3, because I am integrating this out at all possible x2 for some fixed time t2. On the right hand side, I am taking this p1 x1 because this is independent of x2, but these two terms, these two transition probabilities are functions of x2. So this keeps, we have to keep them inside the integral. then what we get here is, we get the marginal distribution function P2 divided by P1. This by definition is nothing but a conditional probability given x1 t1, what is x3 t3, okay. And now we are showing that that is nothing but a product of two transition probability integrated over all x2 possible values. If if the condition probability that we have defined here, okay, if that satisfies this equation, then we say this is a true Markov process. So you have a physical process and you have thought through some time domain and coarse graining, and you say that yeah, this can be a Markov process, and then you define a transition probability. That transition probability will have to survive this condition. Only then this is a Markov process. And this equation is what we call as a Chapman-Kolmogorov equation. It has to survive every x2. So what we are saying is, the only condition for this is that what you are integrating out, that has to be a time in between the 2 points t1 and t3, okay. If I have to show this graphically, what this equation basically means is, suppose you have time axis t1, t2, t3, okay. These are the possible values of x, x1, x2, x3, okay. Think of this as a one-dimensional axis of a Brownian particle motion, Brownian coordinates. So x1 can be found anywhere, x2 can be found anywhere here, x3 can be found anywhere here. Time goes like this. Now what we are saying here is, this is the transition probability, that given that it is at x1 at t1, what's the probability I will find at x3 t3? What's the probability given that this, what's the probability of finding x3 at t3? This is what this quantity will tell you, and we are saying that quantity will be nothing but various possible routes. So in this trajectory, it has taken this particular x2 value, and from here it has jumped to x3. This is one possibility. I can do another possibility, and this integral actually means I am taking every possible value of x2 through which it will go here, okay. Then this transition probability should satisfy every possible intermediate values, then only this is valid. Suppose if this is not the case, that means your transition probability has a memory, okay. It does not represent a Markov process completely, okay. So we take this as a consistency test for a Markov process. Two very important point. A Markov process is defined based on a transition probability that depends only on the current state for its future state, okay. Once you have this, we are able to write any n-point joint distribution function through successive multiplication of transition probabilities. This is point 2. Point 3 is that a consistency test for a transition probability should satisfy Chapman-Kolmogorov equation, which basically means that when you given a condition to x1 t1, the probability of finding x3 t3 can go through any intermediate states that is possible, okay, and it does not depend on this path, okay. So those are the important things you should keep in mind. Okay, we will stop here.